So I guess we will start on time. Welcome everyone to today's webinar. As you know, this is part of the E-Axis Forum on Climate Change, Macroeconomics and Finance. And the aim of this of E-Axis Forum is to facilitate the exchange of ideas on climate change, macroeconomic and finance, and also exchange ideas about policies and research. Very warm welcome to all. It's my pleasure to welcome Nick Muller today, and he's gonna, address a topic which is at the crux of monetary policy, both in terms of policy or monetary theory and policy making, which is the natural interest rate, R star. And you know that R star is, and estimating it is key for policymaker. It's a lot of decisions are taken on this estimation, and whether we are above or below this R star now. It's also a task which is very difficult to achieve. And Nick is going to add more complexity to it, I would say, today by adding environmental issue in the debate. It might be more difficult, but I guess it's also key because adding environmental issue in the estimation of R star is also key to get the right picture about R star and take the right decision. And we'll probably have this is where we'll have a real impact on policy decisions. So before turning the floor to you, let me introduce you more formally. So Nick is the Lester and Judith Lev Professor of Economics at the Engineering and Public Policy at the Department of Engineering and Public Policy and the Taper School of Business at Carnegie Mellon University, which he joined in 2017, and where he directs the Taper School Sustainability Initiative. Nick is also a research associate at the National Bureau of Economic Research and a fellow at the Wilton E. Scott Institute for Energy Innovation. Nick has served on the US EPA's Scientific Advisory Board and the UN Environment Programme panel on co-benefits for climate change mitigation. And his research focuses on measuring pollution damage, market-based policy design, green macroeconomic policy design, and firm valuation net of pollution damage. Finally, Nick has published in a wide range of papers, going from traditional economic journal like the American Economic Review and more, let's say, climate-oriented journal like Nature Climate Change. Before giving you the floor, we have a question for the audience. A few questions for the audience. If you could spend 1 minute answering them. So the first question is, how do you think that monetary damages from air pollution compare to those from greenhouse gas emission produced in the US? And the second, in your opinion, what would be the impact of a green interest rate which increases as emission intensifies fall on transition risks? And also a question of where you're from. I will let a few seconds more for you to answer this question, and I guess the answer would give us a good start to launch the conversation. As usual, you can type your question in the chat or in the Q&A section during the presentation. I will at the end ask them to Nick. And if you have urgent clarifying question, you can also mention them in the chat or the Q&A session, and I will relay them to Nick. So maybe we can see the result of the vote now. So greenhouse gas cost exceeds those of from air pollution. That seems to be the majority. And then, what would be the impact of a green interest rate which increase as emission intensity fall? Then it would reduce transition risk. So happy to to see if you get the same insights, Nick, and the floor is yours.
Great, thank you very much. So are you still able to see the slides? Because they disappeared on my end.
No, we don't see them. If you can share them again.
Let me share them. Yeah, okay. All right, how's that?
That's perfect.
Excellent. Well, let me say thank you, first of all, to the organizers for the opportunity to speak to the E-Axis webinar. It's a real pleasure to be here. I found the results of the poll very interesting, although not that surprising. Those of us in the field of damage valuation know that the relative damages are dependent, of course, on how we measure those damages and certain key parameter choices, some of which I'll talk about today. The typical methods, at least in terms of the social cost of carbon and the valuation of air pollution, suggest the opposite orientation than the poll respondents suggested, which is air pollution damages, at least in the US economy, exceed those from greenhouse gases at the current moment. But again, that is conditional on a number of parameter choices. It's interesting to note the response to the second question, because the very intent of the green interest rate is to manage pollution damage and transition risk as an economy faces a transition in terms of pollution intensity of its output. So that's very interesting. So as Pierre noted, I'm Nick Muller, and I will be talking today about the green interest rate. See, my slides aren't advancing here. There we go. So to many in the audience, it's probably not surprising or news that central banks and financial regulators are increasingly focused on environmental risks to both the financial system and the macroeconomy. There's lots of interesting work and discussion of those points in the recent literature and the popular press, as you can see here. This paper proposes one way, not the only way, but one way to operationalize management of climate and environmental pollution risk through monetary policy. It does so by introducing what I call the green interest rate, which is a conceptualization of the natural interest rate that transmits information on pollution damage to both borrowers and lenders. The basic premise is that the green interest rate, by conveying that information on pollution damage, reallocates consumption to periods when pollution intensity of output is lower, so when the economy is cleaner. And we'll go into this in a lot of detail in a little bit. And the punchline is that the maximum impact of this particular policy instrument occurs when pollution intensity is changing rapidly in an economic system. So when does that occur? Well, it occurs at least in three periods, three settings that manifest in this paper and its empirical application, and there may be others. First, I find that the green interest rate has a significant effect on total pollution damage when, or slightly before, an economy introduces binding environmental policy. The example I will leverage in this talk is the introduction of the Clean Air Act in the United States, which was in the it actually passed in 1970 and was implemented in the years that followed. And that brought about significant changes in pollution intensity in some of the major industrial sectors like utilities and power production, heavy manufacturing and transportation. So that's one broad classification of settings in which pollution intensity changes when new policy happens. Second, during periods of rapid technological innovation, I would argue that we are in, as a global economy, we are in one of those periods now with the onset of renewable technologies, batteries and electric vehicles, automation, and AI. And three, there is evidence that the business cycle, at least insofar as the US experience with the business cycle is indicative, there is evidence that recessions in particular exert a significant cleaning up effect on the economy that is persistent after the economy exits its recessionary periods. And I'll talk about this at more length when we get to the empirical results. So these periods, new policies, rapid technological change, the business cycle, align with risks that were specifically identified by the US Federal Reserve's 2020 Financial Stability Report as being potentially associated with some of the climate and environmental risks that report identified. These periods also align with the concerns of the Network for the Greening of the Financial System, or the NGFS, which expressed concerns about ensuring an orderly transition to a low carbon economy. Again, so look at our examples up above: binding environmental policy, low carbon technological innovation. Those clearly speak to the NGFS's concerns. Because of this, because of where the global economy finds itself, this idea of a reconceptualization of the natural interest rate that builds in non-market pollution damage may be crucial in the current global macroeconomic context. That is, this might be one of those times when we see pollution intensity changing rapidly enough where such a tool could make a difference. So, as I've said, the green interest rate is essentially based on the natural interest rate, or R star. And there are two natural linkages or conceptual links between R star and RG. One is the notion of potential output, which is fundamental to R star. And two is the measurement of trend growth in output, which is also a strong determinant of R star as it's commonly construed. So for instance, Laubach and Williams, whose most recent updates to the empirical R star data sets for the US I use later in the paper, state that the natural interest rate is the real short-term interest rate that's consistent with the economy operating at its full potential. Similarly, Marvin Goodfriend states that the natural interest rate is that which makes desired aggregate lifetime consumption plans conform to present and expected future potential output. So this paper really fundamentally is about asking, what is potential output? And the key here, the contribution, the connection that this paper makes to a long-standing literature, is the contention that potential output is mismeasured if we don't consider pollution damage. In particular, those impacts that are outside of the market boundary and therefore aren't encompassed by our standard accounting aggregates. As I said, this idea that output and potential output is not comprehensively measured is an old idea. It goes all the way back at least to the seminal work of Bill Nordhaus and James Tobin in 1973, and their first attempt to empirically estimate augmented accounts, one dimension of which included pollution damage and the value of natural resources. And this literature has, of course, matured over the years. But just notice that I'm making a connection between an existing idea, reconceiving how we measure the accounts and output, and the idea of R star as this potential output realizing interest rate. So how big is this mismeasurement? Well, the recent empirical literature suggests it's not small in the US, and it's potentially larger in other economies. So damages from CO2 and the air pollutants that I'm going to talk about today amount to about 5% of US GDP in 2017, subject to modeling assumptions, which I'll talk about later in the talk. Pollution intensity is much higher in China. It's about double that in 2018, the most recent estimates that I'm aware of, and it's approaching that in economies like India. So this is not a trivial recalibration of what is potential output. As I said, so this is a non-trivial adjustment. The second piece, this linkage between how we typically think about R star and the green interest rate, is that a key driver of R star is trend growth in potential GDP. And so the same arguments above regarding mismeasurement and output levels are going to apply to growth estimates as well. And so again, I'm going to ask, how big is this adjustment? Well, when you look back over 60 years in the US economy, again, specifically thinking about pre and post environmental policy in the Clean Air Act, my estimates from a previous paper suggest that the difference in growth between GDP as traditionally measured and GDP less pollution damage is as much as 150 basis points. And that maximum difference is right around before and after the Clean Air Act gets passed, and pollution damage was rising rapidly, and then it started falling rapidly thereafter. So again, I'm looking to the literature and saying, well, how big is the correction in levels? In the US economy, it might be as much as 5% currently. It was more than that in the past. And how big is the adjustment in terms of growth rates? Well, it's smaller right now, but in the past, it was much bigger. And what can we learn from these lessons as we think about recalibrating to a green interest rate like metric? So what does the paper do? I estimate the green interest rate by deducting air pollution and CO2 equivalent damages in the US economy. I deduct those from GDP to estimate environmentally adjusted value added, or EVA. I do that from 1957 to 2016. There's some data issues that take me back to 1957 and not before then. This time period, the 60-year time period, includes, as I've said, the passage of the Federal Clean Air Act in 1970, which was the key transition point from the US economy moving from a period of rising pollution damages to falling air pollution damages. Incidentally, the Clean Water Act, the Federal Clean Water Act, was passed just a couple of years later. And though I'm not aware of work like this in the water pollution space, I would be pretty confident that we see the same trajectory. Where we don't see that trajectory, as we'll see in the empirics, is with CO2. So as I said, this was a transition period. It also led to lots of technological change in utilities, heavy manufacturing, and transportation in order to comply with the Clean Air Act's mandates. And this series also includes other significant macroeconomic episodes like the energy crisis in the mid-70s, the financial crisis in 2008, 2009, and the recession in the early 1980s, where a significant portion of heavy manufacturing in the United States shuttered and moved offshore rather. So lots of macroeconomic turmoil, if you will, in this time series. And that gives a nice sense of how policies and the business cycle interact in terms of dictating pollution damages and RG. So just a preview of results in case we don't get all the way through. Number one, on the conceptual side, I introduced pollution into a new Keynesian model on the supply side through a measure of the pollution intensity of technology used to produce output, together with labor. I solve for the green interest rate, just like we would develop expressions for R star, by aligning consumption with full potential output, both without pollution damage to generate an expression for R star for comparative purposes, and with pollution damage deducted for the green interest rate. And what falls out of that exercise is that the green interest rate depends on the intertemporal changes in pollution intensity of output. It doesn't depend on the levels. It depends on the change in pollution intensity. And it depends in the following way. When the economy is growing dirtier, the green interest rate falls relative to R star. And when the pollution intensity is falling, when the economy is cleaning up, the green interest rate rises relative to R star. Now, why is that the case? Well, when pollution intensity is rising, what we would like to do is to draw consumption from the future when pollution intensity is worse back to the present, because that's a lower pollution intensity period by definition of pollution intensity rising over time. And to do that, we want a lower real interest rate that's going to stimulate near-term consumption relative to near-term savings. Conversely, when economies are cleaning up over time, what we want to do is save a little bit more, delay consumption, and release that consumption in the less polluted future. and hence we want a slightly higher real interest rate. And that's the conceptual linkage between what falls out of the model. So previewing the empirical results from 1957 to 2016, damages in the US, this is combined CO2 and air pollution damages, fell by about 0.35% annually in real terms. It's a pretty rapid rate. As a result of falling pollution damage and rising GDP per capita on average, we find that the adjusted indicator, where you take gross domestic product and deduct off pollution damage, or EVA, the growth in that adjusted measure exceeded GDP growth by about 50 basis points on average. We'll see there's lots of heterogeneity in that difference. Accordingly, on average, over this 60-year time period, the green interest rate exceeds the Laubach and Williams estimates of R star by about 50 basis points. So again, remember from the previous screen, the conceptual modeling results, when economies are cleaning up, we want to delay consumption and release it into the future when there is less pollution intensive output, and therefore to reduce total damage from consumption. And that's what we find coming out of the empirics, is that RG on average is higher than R star. However, the orientation between the green interest rate and R star changed in 1970 upon passage of the Clean Air Act. From 1957 to 1970, damages in the US were rising relatively rapidly. And therefore, when I compute the green interest rate and compare it to the R star estimates from the literature, the green interest rate is less than R star by about 150 basis points. Pollution intensity is rising at this time. And then in the 1970s, when the act was passed and all of the changes in the economy started to be implemented, the damages started to fall and RG exceeds R star by about 150 basis points. What I will say is from the 70s to today, to 2016, that difference has been attenuating over time as pollution damages have continued to fall, but the degree of pollution intensity has fallen as well. And so the gross difference between the rates then is attenuating over time. I also find that the business cycle is an important determinant of the comparison between the green interest rate and R star, with during recessions, the difference between the green interest rate and R star being about 2 times larger than during expansions. This is an interesting question for further research, but during this time period, when there are recessions in the US economy, the economy goes in at a certain level of pollution intensity and comes out with less pollution intensity, and it tends to stay at that lower level. And I think there's a number of reasons why that might be true, but actually pinning down why that's true, while beyond the scope of this paper, is something that would be interesting for to look at in future research. And then what I do at the end is just some very simple provisional simulations to try to estimate how much the damages are reduced by the implementation of the green interest rate. So I simulate consumption with the green interest rate and consumption with the conventionally estimated R star, and I compute the change in damages, or I estimate the change in damages. And what I find, not surprisingly, is that the biggest effect is in the period leading up to the passage of the Clean Air Act. That's when the effect of this non-traditional environmental macro policy instrument takes its largest effect. Okay, so the remainder of the talk, I will spend a little bit of time going through the theoretical model just to derive the expressions for the green interest rate and R star, and to compare the two. I'll talk a bit about empirical modeling, keeping my eye on the time. I will then talk about both the theoretical results and the connection, more importantly, between the empirical results and the theory model, and then I'll wrap up with some discussion points. So as I said, I'm using a new Keynesian representation of the economy, where households maximize 2-period utility, subject to a budget constraint, where R is the real interest rate and rho is the pure rate of time preference. I assume power utility, and then the optimization process yields the familiar Euler equation. On the supply side of the economy, there's much more detail in the paper, of course, if anybody's interested to dig into the details. I'm relying heavily on Marvin Goodfriend's characterization of the new Keynesian model. Output of market goods and services is produced with a technology and labor, and in equilibrium, we can characterize output as a function of technology at time period t, shown by A, the curvature in the production function, or psi, and the markup u. Now, what I'm doing that's different is to deduct pollution damage from our measure of technology, which is A. And so to do that, I'm going to introduce a little bit more notation. So notice that the product of A times 1 minus these additional terms is going to give you output net of pollution damage. That's the first thing to notice. That parenthetical term is going to show up over and over again in the expressions for the green interest rate and the difference between the green interest rate and the natural interest rate. So I want everybody to be comfortable with what it's showing us. In the inner parenthetical term, the alpha t term is just the pollution intensity of output. So this would be capturing whether an economy is predominantly powered by, say, coal versus natural gas versus some mix of natural gas and renewables. The beta term is characterizing the responsiveness of damages to investments in pollution control or abatement. And the fraction of output allocated to abatement is controlled by the gamma term. And so again, the product of A and that inner parenthetical term is just going to be damages net of pollution control. So this is what I would observe in the emissions data, and therefore what I can estimate. And then A times 1 is just A. So A minus pollution damage is going to give us that net output measure. All right. And so to derive our expressions for the first R star, what I'm going to do is assume log utility, which I realize is an assumption. I'm going to substitute in potential output, just like I've shown here, in periods 1 and 2 for consumption in the Euler equation. And then I'm simply going to solve for R star. And that's the interest rate that's going to equate our period 1 and period 2 consumption with period 1 and period 2 potential output, conventionally defined without pollution damage. And so when I do that, I get a very simple expression for R star that is increasing in the rate of technological progress. That's A2 over A1. It's increasing in the pure rate of time preference, and it's declining in the markup. And this expression is almost identical to what Marvin and others have derived in the new Keynesian framework for the natural interest rate. Now, when I, instead of using the measure of potential output that ignores pollution damage, when I bring pollution damage in and I repeat that exercise, I get a slightly different expression for the green interest rate. And the difference is essentially the second parenthetical term, the ratio of pollution damage intensity in period 2 to period 1. Okay, so I'm going to highlight and isolate that term on my next slide. So it's not going away. I want to talk about it some more. So if I characterize the ratio of 1 plus the green interest rate to 1 plus the natural interest rate as conventionally defined, the difference is that ratio is just that change intertemporally in pollution intensity. And the value that that ratio is going to take on or assume is greater than 1 when the economy is cleaning up, because the inner parenthetical term on that numerator is going to be smaller than the inner parenthetical term in the denominator, and therefore 1 minus that smaller term is going to be larger than 1 minus the larger term, and that's going to give us a value for that ratio that's greater than 1. And that means that's going to boost or enhance RG relative to R star. Conversely, an economy that's growing dirtier over time is going to have exactly the opposite effect. This term is going to have exactly opposite effect. It's going to attenuate RG relative to R star. Okay, so just summarizing the key punchlines from the conceptual model. pollution intensity rises. When pollution intensity is rising, the green interest rate is falling relative to R star. What does that mean? It's drawing consumption into the present from the dirtier future. Simple intuition. And just the opposite holds when the economy is getting cleaner over time. Now, the last thing I want to show you, there's a lot of notation here, but I just want to concretize my damage simulations that come at the end of the talk. In period 1 and period 2, I'm computing the difference in damages. So that's the A1 term times the inner parenthetical term, alpha minus beta gamma, for period 1 with the natural interest rate and the green interest rate, and then doing that again in period 2. And I add up those damages to assess how damages have changed over time. All of this modeling is calibrated to the US economy as it moves along from 1957 to more or less the present. We'll see the results of these empirically in a little bit. Okay, so on to the empirical modeling. What I'm computing has been called in prior literature gross external damage. So this is the premature mortality damage from PM 2.5 exposure, which is a good index for total air pollution damage. In lots of prior work, it's been found to this particular endpoint and the precursor emissions that are associated with it have been found to account for something like 90 to 95% of all air pollution damages in the US. So this is a good one way to capture a large share of total air pollution damage. And then I'm also including CO2 damage, and I'll talk about how I estimate these in a minute. When I compute local air pollution damages, I am using very common approaches to attribute mortality risk to PM exposure and evaluation of mortality risk. These parameter choices and the models that I'm using have been used by EPA in other settings. They've been used by other academics in similar contexts as well. To value CO2 emissions, I'm using the social cost of carbon estimates from the updated federal interagency working group. These are about $40 to $50 a ton in current dollars. I'm sorry, in current time periods. They're much smaller than that when you go back to 1957. And I'm simply multiplying that marginal damage, the social cost of carbon, times reported annual emissions for the US economy. And then, as I said earlier, I'm deducting damages from GDP per capita. So damages are, of course, on per capita terms as well. And this is an approach to adjustment of our the NIPAs that goes back many years in the environmental accounting literature. So the air pollution damage, the air pollution data, and I just need to be careful about time. So I'll go a little bit quickly through the data here. So I'm sure I have enough time to present results. And if there are questions about the data in detail, I can come back. Suffice it to say that 1957 in terms of air pollution data and monitoring data is a long time ago. And so what I've had to do is to splice together some series that gives me the contiguous 1957 to 2016 data series. There is a monitoring network that gathered what are called TSP data. This is total suspended particulates, of which PM 2.5 is a subset, back to the late 50s in many of the US's major cities. Where I am, Pittsburgh was certainly one of them. And what I do is then to use regression analysis to take observed PM 2.5 levels from the monitors in the present, in the modern era, I should say, and regress that on TSP that is still measured in those locations. So these are concurrent regression of concurrent data on concurrent data for TSP. And that gives us a plot that looks like the following, where the solid line are the TSP readings. These are in micrograms per cubic meter. And the dashed line at the bottom are the PM 2.5 data. From 1980 forward, we have that data. From 1980 backward, we have the estimates. And you can see the estimates along with their confidence intervals shown on the left-hand side of the graph. I'll just take a moment here because I love these data. Notice the vertical lines are marking official NDER recessions. And you can see, for instance, the double dip recession in the early 1980s, the remarkable decline in TSP readings. Something like 10 to 15 micrograms were lost in our annual average data that corresponded with the closure of lots of manufacturing facilities. And you'll notice when the economy picked up in the 1980s, the TSP levels didn't really pick up. And you can see that again going over the 1990 recession and in the Great Recession just prior to 2010. This theme is really present in the data, and it's an interesting one to consider. Okay, so that gives us our series up to 1980. And then for the 1980 to 2016 period, we have high resolution satellite data that gives us a really spatially comprehensive readings on PM 2.5. We geolocate those, and we can match that to the pollution monitoring data in cities, where we only have the 1999 to 2016 series. And so what this gives us, the regression coupled with the satellite data, is the full 1957 to 2016 PM 2.5 series. Okay, so linking PM 2.5 exposure to premature mortality, and I see I should probably speed up. I'm getting too involved in the data. Uses the following functional form. I guess the most important thing to say here is that this is what's used in all the benefit, cost, and regulatory impact analyses that the US EPA does for air pollution. So there's literally nothing exotic that I'm doing here. The VSL choice is a critical choice, and the functional form choice here is a critical choice. As I said, the functional form choice I'm using has been used by many others. You don't see the VSLs used in federal regulatory analysis going back to 1957. So let me just emphasize that from the mid-90s to the present, I'm using what would be considered very standard VSLs. From the mid-90s back to 1957, I am using empirical evidence of the VSLs gathered from US labor market data in a paper by Dora Costa and Matt Kahn. So I would think that would be about the best estimate you could get of a VSL in the US at that time, coming from the VSLs estimated in labor market data in the US itself. This gives us a real VSL increasing from about 2 million to about 10 million over this 60-year period. It's shown by that black line. Okay, now the final data piece before I get to results is the social cost of carbon series, which is shown with the diamond shapes, increasing at about 1% per year, and the CO2 emissions data, which are shown with the solid black line. This is coming from the Department of Energy. Highly pro-cyclical series, peaking during the Great Recession of 2008, 2009. Okay, so on to results. The first thing I want to show you is how the damage series behave. And so the left-hand panel of this graph is showing you three things. The heavy black line is just GDP per capita. These are all indexed to their values in 1957. And so you can see GDP per capita increased by about a factor of 3 over this time. The dashed line that's slightly above GDP per capita are CO2 damages, and those are increasing along with GDP per capita in very much a pro-cyclical fashion, increasing at about 1 to 1.5% in real terms over that time. So it lies above the GDP per capita trend. But then the third line that ends up lower, the dashed dotted line, are the real air pollution damages. And what's so interesting about these is you go from 1957 to the late 1960s, this looks just like CO2. It's an unregulated pollutant. Damages are rising with economic growth. Then the Clean Air Act is passed, and the constraints start to bind, and the damages start to fall, and they fall relatively monotonically down to the present, where they're about 25% below where they were in 1957. Notice again the importance of some of the recessionary periods, the Great Recession and the 1980 recessions, in triggering these big drops in damages, where the damages then did not for air pollution subsequently return when the economy began to expand. I'm going to have to forgo the right-hand graph in the interest of time. Here are the interest rate comparisons. So I've put the federal funds rate in just as a point of reference. R star values are taken from Laubach and Williams. The RGs are computed in the paper. And so you can see over this entire time period, excuse me, R star averaged 3.1% and RG averaged about 3.6% for a difference of about 50 basis points. You can also see that there's significant heterogeneity, as I've been alluding to over this time period, according to before and after the passage of the Clean Air Act. 1960s, the difference was the natural interest rate was larger than the green interest rate by about 150 basis points. After the passage of the Clean Air Act in the 1970s, the difference was 150 basis points, but the orientation between the two flipped. And that's strictly a function of the fact that damages were rising, both CO2 and air pollution damages were rising in the late 1950s and 1960s. And then the act is passed, manufacturing, power production, transportation start to change, damages start to fall, and we see this reorientation of RG and R star. And then you can also see the pattern that I alluded to earlier where the difference is attenuating over time. And so one might say, well, geez, here we are, look at column 7 in the 2010s, the difference is 15 basis points, what's the big deal? And just looking at this paper, that's a totally reasonable conclusion that we're in a space where the difference isn't very large. One of my concluding thoughts, and I just want to lay it out there now, is if we are in a position where the global economy, let's be honest, the US economy, starts to enact binding climate policy, given that the EU and others around the world have indeed enacted binding climate policy, these numbers may start to spread apart again, right? As damages either begin to fall faster, or if climate damages really ramp up quickly, like we hit a tipping point, then these differences are going to spread apart in the opposite direction. With damages rising rapidly, R star would exceed RG again. Here's a graph of what I just showed in the table. So the black line is the federal funds rate. The dash dotted line is the estimates of R star from Laubach and Williams, and the dashed line that's rising at first and then falling is RG. And you can see the vertical line is the passage of the Clean Air Act. You can see how crucial that is, that legislative intervention, to the orientation between these two interest rates. Okay, this table is looking at the influence of the business cycle on these differences. And what I've highlighted here are all years in recessions, column 2, and all years when the economy is expanding, column 3. And if you look at the bottom row, you can see that the difference, RG minus R star, is about 90 basis points during recessions. Damages are falling rapidly in those periods, and we've seen that a number of times in the air pollution data strictly and in the damage graphs. And then during recessions, you can see that RG is still in excess of R star on average, but the difference is much smaller. It's about half as large. Now, over on the right-hand side of the table, there aren't a lot of years prior to 1970 in the data, so it's hard to draw meaningful conclusions. But column 5 is suggestive that the business cycle and expansions in particular, prior to the enactment of the Clean Air Act, were associated with rapidly rising damages and big differences between R star and RG, with R star exceeding the green interest rate by something like 180 basis points. Rapidly rising damages gives us this difference. And then interesting, in column 6 and column 7, the difference across the phases of the business cycle between these two interest rates is much, much smaller. And that's the dampening effect, I would argue, of the Clean Air Act on the air pollution damages during expansions. You know, the strict limits, that the standards are in place, and so there's growth, but the growth is limited in terms of air pollution by those constraints. Okay, I see Pierre. Pierre, should I hurry up a little bit? Should I wrap up? Oops, I can't hear you. I think it's my headphones. Hang on one sec. Go here.
Try again. One more thing. My headphones have been acting up lately. All right. Now,
Maybe
time?
maybe you can hear me now. Huh?
Now I can hear you.
Yeah. Sorry. Like, if you want 10 minutes for the question, you should wrap up in the.
Okay. So let me move on to my conclusion slide and just note what I did at the outset of the talk, which is that central banks and financial regulators are attuned to environmental risks to the financial system. This paper operationalizes one way to think about the management of climate and environmental risks. It does so with this green interest rate, and you know how the green interest rate works, and you know when its maximum impact occurs. The three things I want to emphasize moving forward are the potential lessons from the passage of the Clean Air Act for near-term climate policy passage in the US and how that would work with the green interest rate. The second is the importance of the business cycle and whether there are lessons to draw from the COVID-19 pandemic coming in and out of that recession. And then the third is all the data and methodology to do this in an official federal sense or in a multinational sense is available. These are peer-reviewed methods, publicly available data. And so it's all there and available to be done. So thanks everybody for your time. Pierre, would you suggest I take my slides down or leave them up? What would you like?
I think if you can take them down and please.
Absolutely.
Excellent. Thank you very much. Fascinating presentation. I have a few questions on my side, but if the audience want to ask question, there is a Q&A box where you can do it. One of my questions, so can you hear me, Nick?
Okay. Yeah.
I mean, if I understood well, the way you integrate the cost of pollution is really directly into a change in production, basically. So there is no like welfare impact due to externality. So in a sense, what you mean is that if the Fed uses one, try to compute the biased picture of what is the, they constantly have a biased picture of what is the interest rate, the potential interest rate.
Yeah, so let me make sure I understand. You froze for a minute there, which is probably on my end, but I'm pretty sure I understand the nature of the question. Let me just rephrase. So pollution is entering on the production side. There's no direct welfare impact of pollution damage. And you're wondering whether that particular representation of how pollution enters the model is going to give us a biased depiction of its influence on the green interest rate. Is that a correct?
No, I mean, one way is to say, like, if the Fed is estimating R star without the damages, as explicitly taken into account the pollution damages, then they will have a constant bias picture about the potential output and the natural interest rate.
Yeah, so they will. The key here is that at least on the air pollution side, the vast majority of the damages in monetary terms are non-market. And so this is the imposition of mortality risk that there is significant and long-standing evidence that there is a willingness to pay on the part of households and consumers to avoid, which means if potential output is focused on the NIPAs are not capturing this valuable risk that's being imposed on consumers and households, right? So if, say, these risks were manifesting in the labor market, and all of that was captured by the NIPAs, because we would observe the suppressed labor productivity because of exposure to pollution, et cetera, then the only thing that would be wrong in that case would be the allocation of output between the polluting and the non-polluting sectors. But that's not the case. What we see is, as I said, something like 85 to 95% of damages are occurring in this non-market risk valuation piece, which is not in the NIPAs, which means there is a biased sense of potential output coming from the NIPAs and the accounts. Crucially, though, what this paper says is it's not constant, it's changing over time. And the way in which it's changing is a function both of policies outside the Fed's purview, that is the Clean Air Act and environmental policies, and the business cycle. And it's that latter piece that is probably the most explicit connection between RG and the Fed's usual roles, right, in managing stability. But I would also argue that the influence of RG on the non-market damages itself, which the simulations show, is also an expansion of the role to include management of risks that would typically be outside the Fed's purview. But if we think about, say, climate damages moving forward as being a contributor to instability, then I'm not really arguing for an expansion of the role. I'm arguing for an expansion of the ingredients and components that go into the role. That is, what is risk.
And if I come back to your slide where you compare the evolution of RG, R star, and the Fed fund. So basically, currently, if the real potential output is RG, because R star is not taking into account the losses from pollution, then we would have that the Fed is now basically having a even more expensive expansionary monetary policies that it should, that's right.
Yeah, that's right. Right now in the US, the difference doesn't look too big, right? I mean, if we tend to think about changes in 25 basis point increments, we're within that range right now. My contention, as I said during the talk, though, is moving forward, if we encounter thresholds or tipping points in climate damage themselves, or if we encounter significant changes in production processes coming from transitions to low carbon technologies mandated by policy, those two rates are going to spread apart again. And it's at that time, as I draw an analog back to the 60s and 70s, it's at that time where this difference makes a much bigger effect than it would currently, to the tune of 15 to 20 basis points.
And last question, a bit prospective. So let's assume that now we will see a transition to a low carbon economy, so kind of a cleaning up of the economy in the future. It's basically, so in terms of consumption, with your model, we should be now consuming less than in the future. So in a sense, from a macroeconomic perspective, if we have a transition, there is a high likelihood that we will see increased consumption in the future, so that the transition will be accompanied by a higher consumption and by a higher interest rate as well. Yes.
So if the trend is one that continues towards decarbonization and reduced damages relative to output, the green interest rate would say slightly higher signal, would set a slightly higher signal than R star. And the implication of that would be slightly more savings now and more consumption in the future when the economy is cleaner. It's important to note that these are, at the 60s and 70s is an exception to this statement, but these are relatively incremental differences, but the nudges collectively make a significant difference in the damages. And if the damages are manifesting for climate change in things like future property value changes along coastlines, those are key ingredients in macroeconomic stability considerations, right? And so the degree to which a Fed can use a policy instrument within a traditional space, monetary policy, to attenuate those damages in aggregate, then that seems to be a reasonable step to take when we run the risk of significant damages in the future.
Oh, there's one question from Paul in Barcelona, and I'm reading it to you because I'm not sure I understand what you referred to. So this is that you talk about the CAA as a key policy to reduce air pollution. I don't know what CAA is. Sorry. So
Clean Air Act.
Okay, Clean Air Act too. What about the reallocation of production to Asia for after that? And then the second question from, should not RG consider damages beyond air pollution like environmental disaster, etc.?
Yes. Okay. The Asia point is a really good point. So we have an NBER working paper that came out in the summer of 2020, I believe, that while it did not compute RG, it computed global environmental accounts for 168 countries over 20 years. And one of the findings I want to emphasize speaks directly to that question, and that is from 1998 to 2018, I believe it's the World Bank's categorization of high middle income countries, which now includes China, pollution intensity increased rapidly, right? So why? Well, we know why. It increased rapidly in part because of the phenomenon that the question actually raised, right? Which was offshoring of pollution intensive industries and rapid economic growth in those other areas. So if one were to consider the flows of trade, the differences in pollution intensity across economies in the cross section, then we would need to think as collectively as possible in terms of multiple regulators and central banks in terms of what the interest rates should be calibrated as cross-sectionally, as well as within one economic unit, like I'm doing in this paper in the US over time. That's important to recognize. The second point is the literature on water pollution damages is quite thin. There's some work. That work suggests that the damages are quite small relative to either climate or air pollution. But I fully agree that the green interest rate should in fact include water pollution damage. It should include toxics. It should include solid wastes. We have very good data on air pollution and CO2. So I'm starting here, but in no way am I suggesting, this is the full comprehensive measure of damages. Having noted that, I would remind the person that asked the question that even with just air pollution and CO2, we're still talking about a pretty significant damage intensity measure in the US and a very significant intensity measure in other more developing economies.
Thank you very much. So I promised you to finish on time. We're 2 minutes away from the end. Thank you very much, Nick, for this very interesting presentation. Let me just finish by reminding the audience that our next webinar will take place on October 25th, and we will have Francesco Giudi of the European Central Bank, who will speak about the outcome of the ECB strategy review and the roadmap that they have decided after that. So after, let's say, a theoretical presentation, we will go back to very applied policy making. I hope to see you there on this occasion. In the meantime, just remind you that we have a Slack Slack page where you can interact and ask questions. The community is quite active there. If you want to post new research, ask question, or just get informed about what is coming in the field of financial policy or finance, macroeconomic policy, and climate change, join the Slack page. Thanks again, Nick.
Thank you.
And see everyone in 2 weeks for the next webinar. Thank you very much.
Thank you. Bye-bye.